Good afternoon, everybody. My name is Ken Jordan. I look after the tech support and marketing departments at Chromatograph Specialties. I'd like to welcome you here today. We're going to explore and discuss some recent advances in GC and HPLC detection, specifically those pioneered by Activated Research Company, or ARC. Today's speaker is Dr. Andrew Jones. He's the CEO and co-founder of Activated Research. He graduated from the University of Minnesota Twin Cities with degrees in Chem-Eng and chemistry, went on to receive a PhD in chemical engineering from the University of California at Berkeley. He studied catalysis there. Andrew's the inventor of the PolyArc system, the Jetonizer, and a new product that will be introduced soon, the Solvair. He was recently awarded the prestigious WestTech Award from the Dow Chemical Company, which acknowledged how ARC's products would add value to Dow's analytical research and development and positively impact the technical community. During the webinar, we'd encourage the attendees to mute their speakers. That minimizes background noise. We will be holding a question and answer session at the end of the meeting. If you have questions as we're going along, there's a chat box function on screen that we encourage you to submit those, and then we'll address those and any of the questions that arise at the end of the session. So without further ado, I pass the buck over to Andrew.
Excellent. Well, thank you, Ken, so much for the kind introduction, and thank you, everyone, for attending. I hope you find this useful and informative. So what I'd like to do with everyone today is, there we go, is go through a little bit about this concept of compound independent calibration, what it is, why one should care about it, and how it could be useful to, hopefully, your labs. And then a little background of our company, Activated Research, out here in Minnesota, and dive into the meat of it, which is some of the applications where we're seeing a lot of use for the PolyArc reactor, and then jump into some applications for a in situ catalytic methylation inside of an FID, and finally touch a little bit on our new product, which hasn't been released yet, which is bringing an FID into HPLC for more uniform carbon response there. So without further ado, I'll jump into that. So what we've been hearing, and maybe this resonates with a lot of you, I hope it does, this is what we've been hearing from our customers and scientists around the world, and really drove us to develop this application or reactor to do compound independent calibration, which is not an entirely new concept, but had never been applied to organic or carbon materials specifically. So what we've heard a lot is, we're in the lab, we don't have as much time, that we have more that is being asked of us, and we have more samples. Maybe there's less technical expertise using the GCs, so we need to simplify those GCs. We need to make them quicker, easier to run. And quantification can be a real bear. There's expensive standards, or they might be unavailable, or they just take up a lot of time each day to try to calibrate the instrument. So we looked at these problems that were pretty common in the industry, and we said there's got to be a better way to do this. What if we converted everything in the analyte stream to methane so that you had a uniform detector response with your FID? And I'll get into a little bit what that means in a bit. So Activated Research Company was founded back in July of 2014, and since then we released our PolyArc reactor system and a number of other products. And our passion is really trying to marry catalysis to improve chemical analysis in a wide array of industries and applications. And so the PolyArc was our flagship product, and really speaks to that mission to make chemical analysis more easy by giving a uniform response and a more predictable flow path and workflow. We were fortunate enough to win a number of awards. The first year we launched the PolyArc system, we did win the GCC Best New Product Showcase Award, and we've gone on to win a number of other awards as well, just really helping us showcase the innovation here at ARC and what we've been able to offer our customers. So the PolyArc system is a catalytic reactor, as I mentioned, that goes after your GC column, but before your FID. And this device is built using 3D printing of stainless steel. So that's direct metal laser sintering of stainless steel. And we do that because we want to get very controlled geometries inside of this reactor so that we can do 100% reactions to methane of any analyte without affecting your chromatography. So we don't want to see peak broadening or peak tailing because we know how much work goes into chromatography to make sure that those peak shapes are nice and you don't have co-eluting peaks. So there was a lot of research and development that went into developing a reactor and pairing it with catalysts that could do those reactions to 100% conversion within our ability to measure and not affect your chromatography. So we built that, and it is the first and only commercial 3D printed microreactor out there. So that's pretty exciting to us. How it works is actually pretty simple. You inject your analytes, you separate them through your column of choice, and instead of going directly to your FID, your detector, you go right into your polyarc reactor. We add air and hydrogen to do a sequential combustion and then reduction. So all of your analytes, it could be benzene, gets combusted to a single molecule of benzene would get combusted to 6 molecules of CO2. And then those 6 molecules of CO2 would get reduced with hydrogen to 6 molecules of methane. And in your FID, you would measure 6 molecules of methane. Same thing with ethanol, you'd get 2 molecules of methane from ethanol. And now you have a predictable per carbon response where the FID is going to respond the same because it's just burning methane at that point. So all of those molecules that start to reduce the response in the FID, when you look at oxygenates or chlorine or nitrogen-containing compounds, those all reduce the ability of the FID to burn effectively and create CH plus ions and electrons. When we convert them to methane, we now increase that sensitivity to really the maximum sensitivity of the FID and give you the same response. So things like formaldehyde, you can see a 10-fold increase in sensitivity, formic acid 100-fold, CO2, and an infinite increase because they're invisible in the FID. And the most important part of the polyarc is the uniform response that you're getting because of methane. And that means that quantification is as simple as looking at the relative areas relative to an internal or an external standard. So you do a single calibration with an internal or external standard, and you have an incredibly accurate now quantification of all of those species. It's important to note that anytime you do a calibration, you're actually introducing error into your system, whether that calibration standard was mishandled or made improperly, there is a risk there. And then when you open that and handle it yourself, put it into a syringe, you can lose analytes that way. We have customers who break open calibration standards and half of their molecules boil off because it's a mixture of low and high volatility compounds. So by doing this and sort of circumventing the issue of calibration, you can actually increase your accuracy. And with calibration, you would not know, you would propagate those errors throughout the analysis. So with the polyarc, you can use this one simple equation to get mass accuracy and quantification for your compounds. This does require you to know what your compounds are, so we're not replacing a mass spec. You can do quantification on a carbon basis without knowing the identity of the molecules, but you're only going to get a carbon yield because you have number of methane produced. So if we look at one of the big users of the polyarc is Dow Chemical, and we ask ourselves, why are they using the polyarc? What's important to them? What they're really looking at is more efficient analysis. So that's in QC or plant operations where they don't need to require their lab techs to run these calibration standards anymore. They can much more efficiently run a single calibration and less frequently to get the analysis. It also increases safety and is more green because you have less chemicals around and you're not requiring for scientists to be exposed to certain chemicals. So we do have some customers that are looking at cyanide, which is a difficult molecule when you're talking about trying to create calibration standards. Of course, people don't want to be exposed when they don't need to be. So a large application that we see with the polyarc, and also the topic of a recent ASTM method that was awarded with the polyarc in it, is the VOC analysis in paints and coatings. So you've all probably seen low or no VOC paints, which are waterborne paints. And in order to get that low or no VOC rating, they need to be analyzed for 50 grams per liter or less VOC content, or 5 grams per liter or less for the no VOCs. And what people are now using the polyarc to do is to analyze a number of different solvents in those paints and coatings to determine the quantification of all of those species with a single injection. So the previous method required over 100 different solvents be calibrated for to determine their response factors, and then and only then could they analyze their samples, and that could take on the order of 2 weeks. With the polyarc, you can do in a single injection what used to take 2 weeks and get more data. So here we have a chromatogram from a commercial paint sample, and there's a bunch of different VOCs in there. With the polyarc, we were able to quantify with Sherwin-Williams a number of different solvents with the same exact accuracy or better than the FID with calibration. And you can see there's a number that weren't detected or weren't quantifiable, didn't have calibration curves for with the FID that we were able to quantify with the polyarc. So this is a big step change in the amount of data that can be obtained in a short amount of time. And this is just by the numbers. So the new method, it's ASTM D6886, and there's now a method B that includes the polyarc with it. There was a short ILS that showed an improvement in the reproducibility from 240% down to 70%. So now by using the microreactor and doing a single point calibration instead of multi-point, you can improve your reproducibility, reduce your analysis time, and use less solvents and standards. So it really is a win-win-win all around. And this same sort of methodology can be applied in a number of other industries as well. Here we have a linearity plot for a variety of VOCs. And this just shows the linear dynamic range of the detector. So we're not sacrificing any of the capabilities of the FID. You're still getting your 7 orders of magnitude range, your low 100 ppb lower limits, and your high 100% injection of solvents. You can still see all of those and run those through the polyarc without an issue. This is an important curve that I want to point out. If you look at moles of carbon injected, so this was actually done in an on-column system where the analytes were injected right onto the column. And so you can look at the number of moles of carbon that were injected versus the FID signal. And these data points are from several injections of different concentrations and different oxygenates. And you can see they all lie on the same curve because they're all being converted to methane. So what we're measuring here is conversion to methane and just measuring the FID signal of methane. And this is important because this is your universal calibration curve right here. And you can see with the FID there's some variability. This is a log-log plot, so those are actually pretty big changes. So another application that I want to point out and talk about today is extractables and leachables. So if you're not familiar with extractables and leachables, it's a method for looking at how much of the chemicals that are present in polymers and coatings actually leach into the products that we use, medical devices, pharmaceuticals, even food packaging. And it's a real hot topic right now. There's not a ton of clarity on exactly how these analyses are supposed to be done. So it's left up to the companies in charge to sort of decide how they want to do it. But the big question is, what is coming out and how much. And the difficult question is really, they're both difficult questions to answer analytically, but the quantification aspect is particularly difficult because some of these compounds don't have standards available, and there's a wide variety. There's over 10,000 different additives to plastics alone for different things like thermal stability, as well as UV stability, flavor, all sorts of things. So it's a really big analytical problem and really top of mind for a number of people. So this question of how do you determine what's in the product is also exacerbated by the fact that you need to understand in an initial screen which compounds are larger than 1.5 micrograms per milliliter before you actually do the targeted quantification. And that is sort of the chicken before the egg, or the egg before the chicken, where you wouldn't know how much is in there if you were just looking at a mass spec response, because those can vary by 10 or 100-fold. And so one thing the polyarc does is let you do that much more easily. So if you were trying to answer this quantification question, you have a number of different tools available to you. You could calibrate with a reference compound. Order the compound if you knew what it was. You could also calibrate with a surrogate compound and look at different concentrations versus signal. You could also tabulate response factors and try to look at those tabulated response factors in the literature if someone has done that. However, all of those methods have intrinsically in them assumptions that this will work for that molecule, and you are not necessarily certain that that will. The last method is compound-independent calibration, and that's where the detector has an intrinsically uniform response to a certain molecule or set of molecules. And this isn't a new concept. This was used in atomic emission detection, a very expensive detector, but it had a uniform response for each of the elements that it was looking for. The sulfur chemiluminescence detector converts everything to SO2, all the sulfur to SO2, and therefore you have a uniform response to sulfur. And now finally the polyarc for organic molecules. So what this does is it brings all of these molecules on a per carbon basis to the same response. So in this work with extractables and leachables, this was a study done with Abbott Labs. Here is a test sample with a number of different extractables and leachables commonly found. This was done on a 5% phenyl column with these parameters, a pretty simple, straightforward method, not a lot of method development here. And you can see the identities of the molecules, which were determined with time of flight. If you look at then the quantification using the polyarc, you can do a single injection and use an internal standard and get a pretty good, very good accuracy, within 10% for all the molecules except for two. And the cyclomethicone, the stearic acid, those two probably degraded in the inlet. Sample beforehand, something we're working with Abbott to learn more about. But what you can do here is in a single injection get very good accuracy for a number of different peaks. If we compare that to a mass spec, we are on the order of between 15% and 90% error with three molecules that weren't detectable at all because of their size and concentration there. So this is with an internal standard, assuming an equivalent relative response factor, just like we did with the polyarc FID. You can improve this, and a lot of people in the extractables leachables business will use either surrogate molecules or a lookup table with response factors. In this case, we use surrogate molecules with 5-point calibration curves, and the errors actually got worse. So obviously, it depends heavily on which surrogate molecules you choose, and with a mass spec, it's very hard to target what's going to have the same ionization cross-section to pick a surrogate molecule. The other reason it's important with the FID, and what we see a lot of our customers doing, is pairing the FID with the mass spec using a post-column splitter. Agilent has a very good purged post-column splitter technology where you can take the end of your column and split it into up to three different flow paths and control the pressure of that splitter with an EPC so that you can have a split ratio regardless of your temperature ramp. And that gives very accurate results, allows you to split, for a lot of our customers, from an FID polyarc as well as a mass spec. And so in a single injection, you can get quantification and identification. And another benefit here is you're getting much higher linearity using an FID rather than a mass spec. The mass spec, because of the way it operates, just can jump around a lot more than an FID, with RSDs a lot higher than what you typically see in an FID. The other benefit here of that pairing and of using a polyarc FID is this predictable response. So if you're looking at E&Ls and you know you only need to target quantify those that are above 1.5 micrograms per milliliter, you would have no idea with a mass spec whether that molecule or that peak that shows up is 1.5 micrograms per milliliter, because the response can vary tenfold or more. There was actually 3 compounds that weren't detected just because of the ionization cross-section differences of those compounds. The polyarc FID, because we're converting everything to methane, you have a uniform response, you have a predictable per carbon concentration response. So you can very quickly screen samples and determine if they're above or below certain thresholds. You also have a pretty uniform limit of detection that essentially only depends on the amount of peak broadening you're having. And again, I just want to remind people, I know I'm going through a lot of information very quickly. If there's any questions at all, please chat them through the WebEx, and I'll try to tackle them during the presentation if I can, or definitely at the end. So we get a lot of questions from customers about, is this going to disrupt my methods? Is this going to disrupt the chromatography that I've worked so hard to obtain? You know, we don't want to, we go through a lot of struggle to get those sharp peaks that are not co-eluting. And the answer is no. This is a FID chromatogram of a 87 octane gasoline with 10% ethanol. You can see we have pretty good sharp peaks. There's over 100 different peaks in this chromatogram. When we throw the polyarc on there, we're getting the same, essentially the same resolution. And this is, I believe, with a 0.32 column here. It would be the same with a 0.25. If you get below a 0.25, we have products that we're coming out with soon that will help with sort of fast GC applications and even sharper peaks. But the polyarc itself will work well with 0.25 and 0.32, as well as 0.53 columns. So you can see here we have very uniform or similar peak shapes. The only big difference here is the ethanol peak, which I'm pointing out. I'm not sure if you can see. Yep. So that has actually increased in area because, again, ethanol is the only, really the only oxygenate in the sample. So that increases because we're converting it to methane, and it burns more efficiently as methane. So one thing I want to talk about that I mentioned earlier was the increase in sensitivity. So are you going to see an increase in sensitivity? That depends on what molecules you're looking at. The FID already does a fantastic job at burning and combusting hydrocarbons, olefins, straight chain hydrocarbons, paraffins. And those are already pretty much a uniform response per carbon to methane as they go through the FID. So you're not going to see a big increase in sensitivity for those hydrocarbons. However, when you start to add oxygen, as you can see with these FAMEs, as you go from a C9 or C14 up to a C9, that oxygen to carbon ratio changes, and you start to lose sensitivity in a normal FID, which means we can gain that sensitivity back by converting it to methane. Same thing with the ethers. With alcohols like methanol, now you're up to about a 50% increase or a twofold increase. And then there's a huge jump when you get down to these small single carbon molecules that have a lot of heterogeneity or a lot of functionality. So formamide, formic acid, formaldehyde, and COCO2, those are molecules that are very difficult and have kind of been forgotten about in the literature for GC amenability because of this. However, when we convert them to methane, now we can see them with the same sensitivity, or 100 parts per billion about, on an FID. That opens up the application space for chemists to look at GC again for these types of molecules. So with that, I want to transfer and shift gears a little bit to our Jetinizer product, because I want to leave some time at the end here for questions. So the Jetinizer was our attempt to take on the methanizer head-on. So the polyarc, when it first came out, we got a lot of feedback that said, hey, this is just a methanizer, you know, this is just going to replace my nickel catalyst methanizer. And they were kind of missing the point that the polyarc, it will convert CO and CO2 to methane like a nickel catalyst methanizer, but it will also convert everything else to methane and give you that uniform response. And so we invented the Jetinizer because we realized there was a market for people that were just looking for CO and CO2, and they wanted a cheap and simple solution to do that. So we invented the Jetinizer, which, again, we utilized 3D printing to create these FID jet, to create the geometries inside, to put our catalyst in there and do methanation of CO and CO2, and even, as I'll show you, aldehydes, such as formaldehyde and acetaldehyde, to make methane and make your FID capable of doing a lot more. And it really is just as simple as taking out your old FID jet and putting in this. It takes about 5 minutes. You heat up your FID, and you're good to go. So some of the applications where this is useful, CO and CO2 have been important in ethylene propylene production, specifically carbon monoxide poisons catalysts at very low levels. Air quality, of course, greenhouse gases, transformer oil gas analysis is another one where levels of CO and CO2 can indicate failures in that transformer oil gas or transformer itself. Renewable fuels, beverage analysis, and catalysis. And typically, TCD has been used, although has a very high limit of detection. Mass spec can be used, but of course there's a lot of, the air leak makes it difficult to get low levels, and formaldehyde is very difficult. And the methanizer has been a go-to in the industry for lower levels. But the methanizer, the nickel catalyst, other than being toxic, it is a bit of a nightmare in terms of piping and heating and shutting down. So we have a number of customers who've used nickel catalysts and poison them often, especially in the transformer oil gas analysis area, where small amounts of sulfur can poison the methanizer and render it useless. So traditional methanizer, as I mentioned, has a lot of tubing in and out, fittings that can become difficult to remove, and over 16 parts with a 2 to 6 hour installation. You can contrast that with a Jetinizer, which is a single part and can be installed in 1 to 5 minutes. It really is just taking off, if you use an Agilent, taking off the castle, taking out the old one and putting in a new jet there, screwing it on. There's nothing different with a standard jet. So if you want to look at some differences between the methanizer and the Jetinizer, you're getting the same CO and CO2 conversion. The methanizer has a very good 7 order of magnitude range, just like our Jetinizer. You're going to install it quickly. The real benefit of the catalyst we're using in the Jetinizer is that we can tolerate different poisons, such as sulfur, chlorine, nitrogen, and there's no extra equipment. Actually stealing some of the heat from the FID, and they're non-toxic, so they can be shipped anywhere around the world. If you work for a global company, this makes it very easy to purchase and share these. Nickel, of course, is one of the RoHS incompliant metals. So some applications in this space, if you look at CO2 analysis, here's a number of different injections over 7 orders of magnitude. You can see the peak shape is very good because it's just right into the jet, so there's no extra plumbing to broaden the peaks. If you now look at a conventional FID jet, this is some work done by Jim Luong at Dow Chemical. So there's a analytical methods and an analytical chemistry article written by Jim Luong about these products. And in this case, he's looking at CO and CO2. That was the, whoops, went backwards there. So this is with the conventional jet. And then with the jetinizer, you can see the additional peaks for carbon monoxide and carbon dioxide. And you can see very good peak shape. There is some broadening, and that's mostly from the column for the propylene propane. One important thing to note about the jetinizer is you don't want to be injecting large amounts of larger than C3 compounds, because you can coke the jetinizer catalyst because it is a reducing only atmosphere. So if you're looking at, if you want to avoid that, you can either do a backflush to prevent those molecules from getting into the jetinizer, or you can use a polyarc to analyze everything. And I will mention about the backflush, there is a little bit of a back pressure from the jetinizer, and you can use that to your advantage to actually drop the inlet pressure and force flow to go backwards through your column to flush out any heavies. So that was a method that was invented by and actually pioneered by Jim Luong at Dow, and a very cool, we were excited to see that cool application for the jetinizer. So another application that was written about in this paper was the carbon dioxide in confined spaces, or specifically in airliners. And this coincided with a news article that had talked about pilots whose decision-making was hampered by larger amounts of CO2 in the cockpit. And so it's starting to become an important issue for the airline industry to look at CO2 in the airlines. And what Jim Luong actually did was took samples during a real commercial flight in the front and the rear of the plane, and actually found about 1,000 ppm difference in CO2 between the two. So if you're wanting to convince your boss that you should get the nicer seat in the front of the plane, you can use some of this data to say, hey, it's going to affect my health and my decision making if I'm doing work on the plane, to sit in the front of the plane with 1,000 ppm less CO2. I also like to think of Jim Luong taking samples on a big jetliner in the front and the back of the plane. I'm not sure what people were thinking when they saw that. So here is another method where you're looking at carbon dioxide and carbonated beverages. So this is important for the soda industry. Of course, the CO2 concentration goes down over time. And finally, flue gas, looking at matrices and just methane and CO2. So I encourage you guys to look at those articles. And the sort of last exciting application I want to talk about is that of formaldehyde in the jetinizer. So this is one that was actually born out of surprise that Jim Luong had looked at. We weren't sure the jetinizer would be capable of this, and it is very difficult to do formaldehyde analysis on any instrument. Most of it's done on LC with difficult derivatizations, difficult calibration. It has been attempted on GC. There are companies that produce standards that do not work, and permeation tubes, for example, a number were tried and from different vendors, and they were off by factors of 10 or more in terms of the concentration that were stated. So it's a very difficult molecule because of its reactivity, and in the case of permeation tubes, questionable sort of models of its diffusion through the permeation tubes. So what Jim Luong had to do was actually heat and create his own samples in a glass bomb. And when he did that, he was able to get very good accuracy within about 5% for formaldehyde, and very nice peak shape, in this case using a DB1 for formaldehyde. So this really opens up a lot of new methods for what is a pretty big hot topic right now is formaldehyde in a number of different consumer products. Moreover, the fact that calibration is so difficult means that most of the ways people are calibrating for and analyzing formaldehyde, they're reporting the wrong values. So this could help, because of the uniform response here that you're getting now, help with getting more accurate and reproducible data. So we've talked about two different products here, the polyarc system and the jetonizer. They're both catalytic systems. They both go after your column. The real big difference is that the polyarc converts everything to methane. The jetonizer only converts small molecules, CO, CO2, formaldehyde. So you're not going to get that universal response for everything with the jetonizer, and you're not going to be resistant to as many poisons or large carbonaceous compounds because you're just in a reduction atmosphere. So when people ask, you know, when should I use the polyarc and when should I use the jetonizer, it's pretty simple. If you're just looking at CO, CO2, formaldehyde, the jetonizer is your cheap and easy way to do that. If you instead want to look at more molecules and need that universal response, then the polyarc is the right application for you. And this is the last slide, which just goes right into, we'll talk briefly about our LC product. So we are, for a long time, we had been asked by our customers if we could do the same thing that we do in GC on LC. And we've been working for a while on this. We've received a number of government grants to do this. And we're hoping to release this here in the next quarter of 2019. And so what we are doing is, in the same way that we convert all of our analytes to methane in GC, we are going to convert all LC analytes to methane for detection in an FID. So bringing FID finally to the LC community so that you can take advantage of that 7 order of magnitude linear range that is really unprecedented in LC. So what happens here is our LC column comes in, and using a proprietary method I can't discuss too much of today, we will remove the solvent, which can be water, methanol, acetonitrile, THF, a number of different solvents, completely and entirely. In so doing, we will also remove some of your analytes if they are volatile or similar in size to the solvents. So that's important to note. But the non-volatile molecules will be converted catalytically to methane so that we can detect them in the FID. And here's some preliminary data with sucrose, which of course doesn't have a chromophore, where we were looking at different ppm levels of sucrose, and of course the linearity with the FID is spot on, and we're able to get down to below. We will be able to get down to ppm levels here. You can see our LOD is about 5 ppm, and we're doing much better than that now. So I can try to answer some questions about that if you guys are interested, but look for that in the future. So with that, I think we have some time here for some questions. So I'd love to hear what you guys are thinking and field any of your questions. So thank you all for your time, and I'll open it up to everyone.